Hello everybody, and thank you for joining me for this immune system talk today. So we're going to be talking about modulating immunity. My name is Lauren Craven-Yempick and I'm a nutritionist based in Brighton and Hove. I run Wild and Wise Nutrition, and today this talk is in collaboration with Vitae International. So Vitae have been in the food supplement market for over 25 years now, and they have a strong focus on science and research. They have a strong team of researchers in the company who work with hospitals and universities, testing their products with real patients and specific applications. So they've been in the UK for about the last 5 years now. Their headquarters is based in Barcelona in Spain, and they're focusing only on the professional channel. So I really hope that the information in today's webinar is interesting and useful for practical applications with your clients. So let's get started. So today we're going to be talking about the immune system. We'll have a refresher on the innate immune system, the adaptive immune system, the complement system, certain foods and nutrients that are immune system modulators, and then we'll talk a little bit about Evita, which is Vitae's immune modulating supplement, the mechanism, the way that it's absorbed, and we're going to be looking at some studies and a clinical case study as well at the very end. So the immune system protects individuals from disease with a layered defense that begins with physical and chemical barriers that prevent pathogens from entering the body. So we're just going to quickly go over those, not in too much detail because I'm sure a lot of you will remember this from studying and use it quite regularly. So the innate immune system is also referred to as the non-specific immune system. So this is basically your immune system at birth. So it's the body's first line of defense in overall immunity, and it's made up of cells and mechanisms that defend the host from infection by other organisms. It's also able to sense a pathogen whenever the system's attacked, so able to notice the difference between self and non-self. So it's made up of mechanical, chemical, and biological factors, in addition to the innate immune cells, which we're going to talk about in a few slides. So mechanical factors, we've got the skin barrier, so epithelial tissue. So this is a very impermeable physical barrier that prevents infectious agents from invading. Desquamation of the epithelial surfaces, which is a fancy word for shedding. So this helps to remove any type of pathogen that might be adhered to the skin, or indeed any of the epithelial surfaces inside the body. So for example, along the esophageal tract. We've also got cilia. So cilia are the small kind of finger-like projections that live on epithelial cells. And the motile cilia, so the cilia that moves, can push any pathogens either up so that they can be coughed up and spat out, or down so that they can be swallowed and they will get destroyed by the stomach acid. So we've also got the flushing action of tears and saliva, which helps prevent infection of the eyes and mouth, and the trapping effects of mucus, which helps protect the lungs and digestive system. It's all quite straightforward. Chemical factors. So fatty acids from sweat inhibit the growth of bacteria. Tears, saliva, and nasal secretions contain enzymes like lysozyme and phospholipase, which are capable of destructing pathogens through the bacterial wall breakdown and subsequent destabilization of the cell. There's also lysozyme in urine, and urine is quite acidic. And sebum contains free fatty acids like lauric acid, and it contributes to the acid mantle of the skin, which is another barrier to microbes. The low pH of sweat and gastric juices, which prevents bacterial growth. And then we've got peptides, which an example of those is defensins. So these are low molecular weight proteins implicated in the innate immunity, and they're found in the lung and gastrointestinal tract. And then finally, we've got surfactants. So these in the lung promote phagocytosis and act as opsonins. So they tag any contaminated or dead cells for destruction by other immune cells. And then biological factors. So we've got the normal flora of the body, which is our microbiome, and it's mainly situated on our skin and gastrointestinal tract, and it prevents pathogens from colonizing the body. This is performed through the secretion of substances that are toxic for the pathogens, or by competing with them for nutrients, or for the attachment to certain cell surfaces. We've got toxic secretions like bile, gastric acid, saliva, and sweat, which are toxic to pathogens. And then, of course, biological molecules that we might ingest, for example, beta-glucans. So the adaptive immune system. So if a pathogen successfully evades the innate immune system, there's still another layer of protection. And adaptive immunity isn't competent at birth, but it's developed over time as we interact with our environment. So when a person comes into contact with a foreign substance, components of the adaptive immunity learn the best way to defend it, and they remember. So an improved response the second time around of being up against the same pathogen permits a faster and stronger response of the immune system. So when the body is under attack, an antigen is produced which tags the specific invader molecule, and this identification marks the attacker for future recognition as foreign or non-self. So it's also called specific immunity for this reason. So I thought we could go through a bit of a refresher of all of the different kinds of immune cells. So on the left-hand side, we've got the innate immune cells, and on the right-hand side, adaptive. So looking down towards the bottom left, so we've got the common myeloid cell, which comes down from the stem cell. Now this can change into things like erythrocytes, which are red blood cells, mast cells, but the ones that we're most interested in are the basophils, the neutrophils, eosinophils, and monocyte and macrophage. So these are granulocytes, and these are the first line of defense cells that our immune system has. So basophils are histamine releasing, so they're similar to mast cells in that sense. Neutrophils they're specialized to kill bacteria, and they're the main component of pus whenever there's an infection. Eosinophils, again, are specialized in killing parasites, and they're also an antigen presenting cell. So that's the same as macrophages and monocytes. These are all antigen presenting. So they'll take an antigen from a pathogen and they'll present it to another immune cell, which propagates the immune reaction. So monocytes are in blood and macrophages are in tissue, but they're a very similar cell. And these activate T helper cells, which are in the adaptive part of the immune system. And there are some specialized cells like Kupffer cells in the liver and dendritic cells in the gastrointestinal tract. They're also in the lungs and the skin and a couple of other places. We'll be mentioning dendritic cells quite a bit throughout the webinar. And these are all antigen presenting cells as well, similar to macrophages, not exactly the same. And then on the right hand side, we have our adaptive cells. So there's the natural killer cell, which is actually, it kind of forms a bit of a bridge between the innate and the adaptive immune systems. Although it's technically part of the innate system, they are lymphocytes, but this is because they lack an antigen presenting receptor, so they can self-activate, whereas the other parts of the adaptive immune system, like the T lymphocytes and B lymphocytes, they have to be switched on by an antigen presenting cell or in another method in order for them to then propagate the immune response. So the small lymphocyte goes into the T lymphocyte on the left and then the B lymphocyte on the right. So it doesn't say in this diagram here, but the T lymphocyte splits into another 4 specialized cells. So you've got the T memory cell, which attacks when they remember an antigen. T cytotoxic, which kills pathogens directly. T regulatory cell, which is it's also called Treg cell, and this will be mentioned quite a lot throughout this webinar as well, which prevents the overactivation of the immune system by shutting down other T cells after an immune response. And then finally, the fourth one is a T helper cell. So there's lots of different types of T helper cells. We've got T helper 1, 2, 3, 17, 0, and this particular cell activates the B plasma cell, which you can see in this diagram here, and the B plasma cell is the cell that produces the antibodies. So, and the B lymphocyte actually splits into two. We've got the plasma cell here, which produces antibodies, but we've also got a memory cell, which, similar to the T memory cell, remembers previous pathogens. So, looking now at TH1 and TH2 balance of the immune system. So the following few slides are very it's like an overview, a general overview. So TH1 cells tend to fight intracellular pathogens, whereas TH2 fight extracellular pathogens. So TH1, so TH stands for T helper. So these are all part of the adaptive immune system. So intracellular pathogens are things like viruses. If you think of the virus, in order for it to replicate, it has to invade a cell and turn that into a kind of virus replicating machine. So it is within a cell. Cancer cells, obviously that's a kind of a fault with the replication of the cell itself. So it's within the cell. Intracellular yeasts and intracellular bacteria like pneumonia, whereas TH2, it's extracellular pathogens, so normal bacteria, parasites, also, so helminths, they're a type of parasite, toxins and allergens. So this is a table which compares TH1 and TH2. So as we said, TH1 is generally intracellular, TH2 is extracellular. TH1 is more pro-inflammatory, whereas TH2 is more anti-inflammatory. And as such, TH1 is more aggressive and TH2 less aggressive. So we're talking here about two different types of T helper cells that are activated during an immune reaction. Now, obviously, if you're affected by a virus, then your TH1 part of your immune system will be upregulated to fight that virus, which is normal. So obviously you're going to have a bit of an imbalance during that infection, but then once that infection has been fought, both sides of the immune system should go back to a balanced base level. So that's a kind of healthy way of looking at TH1 and TH2. However, in some cases, certain parts of TH1 and TH2 can be upregulated. So if you're TH1 dominant, then you're more predisposed to organ-specific autoimmune disease. So this is things like Hashimoto's thyroiditis, rheumatoid arthritis, multiple sclerosis, celiac disease, Graves', you know, a lot of this organ-specific autoimmune conditions. Whereas if you're TH2 dominant, it has been linked to systemic autoimmune disease, so something like lupus, which doesn't affect one particular organ. Now, TH1 has also been kind of correlated with having fewer colds, fewer flus and viruses, and actually lower cancer rates because it's upregulating the part that fights viruses, intracellular bacteria and cancer cells. Whereas if TH2 is overactive, it results in allergy. So there are certain herbs and minerals and hormones and supplements that can stimulate both sides of the immune system. So typically TH1 stimulating things are the kinds of herbs and things that you would take if you had recurrent infections, recurrent viruses. So that's things like astragalus, echinacea, medicinal mushrooms and other types of beta-glucans, stimulating things like Panax ginseng, and also possibly melatonin. So hormones do also have an effect. Whereas Th2 stimulating, things like caffeine, green tea, pine bark extract, lycopene, curcumin, progesterone. So all of those things tend to be quite anti-inflammatory anyway. So that shows that they stimulate the anti-inflammatory part of our T helper balance. So moving on now to a couple of reasons why that Th1 and Th2 system may be imbalanced. So the hygiene hypothesis, I'm sure a lot of you have heard of this before. So it's basically, the hypothesis is that children who grow up in clean environments, washed with antibacterial soap, living in sterile homes that are cleaned with disinfectants, they don't have the same exposure to immune challenges, and they're less exposed to the microbial world. So their systems have fewer opportunities to learn and fully develop their immune system. So what I didn't mention before was that there are certain nutrients that also balance the two sides of the immune system. So omega-3, EPA and DHA and vitamin D are both they support the T regulatory cells, so they don't emphasize either Th1 or Th2. And also certain probiotics like lactobacillus and bifidobacterium, they modulate both sides. So studies have shown that they improve resistance to cancer, as well as allergies and atopic allergies like eczema, that kind of thing. So looking now at the hygiene hypothesis. So on the left-hand side here in this diagram, we've got a high hygiene, low pathogen burden. So this is something that you would see potentially in an industrialized world, whereas on the right-hand side, you've got low hygiene, high pathogen burden. So this is something more in a developing country. Now, DC here stands for dendritic cells. So remember, these are the parts of your innate immune system. They tend to be located in the gastrointestinal tract, also in the lungs, skin, in blood as well. So what's missing from the left-hand side is a regulatory dendritic cell and T regulatory cell. So where we have viruses, bacteria, antigens, and helminths and allergens that our dendritic cells are exposed to, the T regulatory cells and the regulatory dendritic cells are there to ensure that the balance between autoimmunity and allergy, or Th1 and Th2, is maintained. So on the right-hand side, regulatory cells have been developed over a period of time due to the high pathogen exposure, so they can maintain the balance between Th1 and Th2. And this is because regulatory T cells produce suppressory cytokines, and they're part of an anti-inflammatory network that ensures that inflammatory T cells and their downstream effectors, they're kept under control. And T regulatory cells also maintain tolerance to self-antigens and reduce the chance of autoimmune disease. So in this way, we can see why there would be a higher chance of autoimmunity and allergy in the low pathogen, high hygiene environment in the industrialized example. So another example of this is on the left-hand side again, we've got the industrialized world. So exposure to vaccines, excess hygiene and antibiotics results in little Th1 stimulation, which because they have to be, one has to counteract the other, it causes an increase in Th2. Whereas on the right-hand side here, we've got a developing nation, and because people are exposed to a lot of parasitic infections like helminths, they have a strong stimulation of their Th2 responses. So what that sounds like is that both environments should have the same response because Th1 has been upregulated. However, what they find is that helminth-infected populations show little signs of allergic disorders, even though they're seropositive for the allergens. So the difference may be explained by the differences in exposure to pathogens. So a high prevalence of chronic infections results in persistent immune challenges. And this causes us cycles of infection and inflammation, which is followed by the triggering of anti-inflammatory molecules to restrict the immune response. So this enables the immune system to establish a robust regulatory network, possibly the key to controlling allergic diseases, because where in the industrialized world, we have higher rates of allergic responses like asthma, eczema. In developing nations, this is absent. So it's a lot more to do with the lack of repeated infections in the industrialized countries, which means our immune system isn't trained to restrict immune responses after the infection. So another hypothesis is the old friends hypothesis. So this says that the lack of bacterial exposure decreases the resilience and diversity of our own microbiome. So microorganisms like this include soil bacteria, Listeria, Salmonella, which cause protective T helper type responses to occur. And so when our hunter-gatherer ancestors were frequently exposed to a wide spectrum of these microorganisms, our modern lifestyle has dramatically decreased our contact with bacteria, yeast, parasites, and other pathogens and microbes. So obviously we've gone from an environment of rural farming where helminth infections and association with animals was very common, to living in predominantly urban settings where this is very rare. So this is another diagram explaining this. So again, we've got the dendritic cells and the regulatory dendritic cells here, which so we've got the organisms that are recognized as harmless by the immune system, and these cause the dendritic cells to mature into regulatory dendritic cells that drive T regulatory cells. So some of these cells will recognize the old friends themselves and provide a continuous background of bystander regulation. So again, it's the regulatory T cell which is providing the supportive role, and in theory without it we wouldn't be able to detect the antigens and self from non-self. So moving on now to the complement system. So the complement system is a complementary, hence the name, or supportive part to the innate and adaptive immune responses. So it's kind of appreciated that it's a functional bridge between the two parts of the immune system. And it first evolved as part of the innate immune system, but it's also involved in destroying antibody-tagged cells, so it's also part of adaptive. So in healthy individuals, it's active at very low levels in the surveying capacity, just sensing any pathogenic activity, as our other white blood cells are as well. And it's a means of helping elimination of dying cells without impacting host tissue. So it's made up of a number of about 20 complement plasma proteins. The main ones are C1 to C9, and these are mainly produced in the liver. And there are three different pathways in which the complement is activated. The main one is the classical pathway, and this is where the C1 protein, which you can see here in the diagram, binds to an antigen-antibody complex. So here we've got the bacterial cell, and then the antibody that's already been attached to the bacterial cell. So that would have been produced by the B plasma cell of the adaptive immune system. And this C1 then is part of a cascade of other complement proteins, which results in a number of different things. So it causes inflammation, So obviously this involves histamine release, blood vessels become leaky, phagocytes are recruited to the area, and also opsonization, which is just a fancy word for tagging the bacterial cell for phagocytosis, so being engulfed by another immune cell. So in this way, yes, so it tags for destruction, promotes inflammation, and damages membranes of the bacterial cells. So these are some of the complement proteins. So C3 is one of the main ones. So this damages the plasma membranes of cells and some forms of bacteria. Variations of the C3 cell act as opsonin, which is the opsonization, the tagging it for destruction from other immune cells, promotes inflammation, attracts macrophages and neutrophils, and activates mast cells, and then that causes the histamine release, and also forms a membrane attack complex, which inserts into the cell membrane of the pathogen, causing cell lysis, so the cell breaks down. So, as with many things, if it's imbalanced and you have either a deficiency or an excess of complement proteins, then these are some of the ways in which it would show up symptomatically. So a deficiency, obviously this is affecting your ability to fight infections. So you're going to see recurrent infections. So whether it's bacterial or viral, you might see this in clients who were ill very frequently, and that's not just in childhood, that's in adulthood as well. It can also specific genetic mutations can be associated with lupus and rheumatoid arthritis, so that's something to also look out for. Whereas on the other hand, excessive complement activation is a bit like an upregulated Th1 part of the immune system, and it basically causes overactivation. So yes, this causes things like autoimmune diseases, Alzheimer's disease, schizophrenia, macular degeneration, Crohn's disease, very varied kind of picture. So something to be aware of. So now we're going to move into the ways in which certain nutrients, pharmaceuticals can affect the immune system. So so an immunostimulant is a substance that stimulates the immune system by inducing activation or increasing the activity of any of its components. So an example would be flu vaccines. Immunosuppressant does the opposite, so it suppresses the immune system by inducing inhibition or decreasing the activity of any of its components. So this is for things like post-transplant procedures, autoimmune drugs, to prevent the rejection of organs and to reduce the stimulation of the immune system during an autoimmune disease. And then immunomodulators, so substances that modulate the immune system by stimulating the T regulatory cells that we've discussed, and or stimulating macrophage and natural killer cells. So macrophages and natural killer cells are part of the immune system and that won't continue to run wild after activation, unlike other parts of the immune system like the T lymphocytes. So this brings us on to beta-glucans. So beta-glucans are a key component of the Evita supplement, and so that's going to be the main focus of the next half of the webinar. So beta-glucans are found naturally in polysaccharides produced by bacteria, yeast, fungi, and plants. They're not found naturally in the human body and have to be ingested. And the most common forms in nutraceutical preparations are taken from baker's yeast or brewer's yeast, which are very similar. They're both the same species of yeast, Saccharomyces cerevisiae. And then, of course, medicinal mushrooms. So medicinal mushrooms, they produce different beta-glucans. We've got a picture of the structure of the different beta-glucans in a few slides, which is really interesting. So medicinal mushrooms like shiitake, maitake and reishi, they've been used for over 2,000 years as health remedies, but it was only in the 20th century that modern science produced the evidence that the active components were in fact beta-glucans. But beta-glucans work very differently depending on the source and the structure. So beta-glucans in oats, and this is made up of a 1-to-3 polysaccharide with a 1-to-4 side chain. And this beta-glucan is found mainly in the oat kernel. And the benefits of this one include digestive fibre. That's the main benefit, really. So providing fecal bulk and helping to produce short-chain fatty acids. And the effect of this is that it lowers cholesterol. So 3 grams per day is an approved claim to reduce LDL cholesterol and therefore reduce cardiovascular risk. And it can also be applied topically to support wound healing. However, that's not what we're going to be talking about today to support the immune system internally, because this is the kinds of beta-glucans from brewers or baker's yeast. So the beta-glucans in Amino Evita are made from spent brewer's yeast, and they're grown on malt barley and clean spring water with no other nutrients added. It's a natural byproduct of the fermentation process used for beer production. So it's a nice bit of kind of using every part of the yeast. The final product, of course, doesn't contain any gluten, and I would say also that if you have a sensitivity to yeast, it won't be an issue because it's an isolated extract of beta-glucan, so it doesn't necessarily matter how it's been, the source. So actually, before we go on to this, just a little bit about how the yeast is extracted. So following autolysis with the yeast's own enzymes, high-performance centrifuges are used to separate the yeast autolysate into the soluble yeast extract and the insoluble yeast wall. So yeast cell walls contain about 30% of beta-glucans of dry weight. So this is obviously what we want. And then during several separation processes, the beta-glucans are further purified without the use of strong alkalines, and soluble compounds are removed. So it's important to mention that the process doesn't involve an acidic hydrolysis, which leaves the acid-sensitive 1-to-6 side chain mainly intact. So you can see this here. So trees have beta-glucans, so that's the top one here, and this is a linear structure. Oat and barley, which are the ones, the beta-glucans which are mainly used for reducing cholesterol and digestive health, they have a twisted linear structure. Algae, there's beta-glucans in algae, and then so the bottom two are the two types of beta-glucans which positively affect the immune system. And interestingly, you can see that they both have the same written structure. So they're both beta 1-to-3, 1-to-6 side chain. However, the structure of both of them is quite different. So medicinal mushrooms, they have a branched structure with only a single glucose unit coming off as a side chain, whereas baker's and brewer's yeast, they have the long side chains, and this is thought to be the structure that has the most effective effect on stimulating your immune system. So it's important that those parts remain intact. So from studies, this particular form of beta-glucans, the 1-to-3 with a 1-to-6 side chain, is deemed to be most optimal for stimulating and supporting the immune system. So it's recognized by intestinal mucosal cells, and the receptor on phagocytes binds to this particular beta-glucan, which is key to activating dendritic cells. So remember, these are the antigen-presenting cells that line your gastrointestinal tract and your lungs, which induces T cell response and cytokine release. So the ways in which the beta-glucan activates our immune cells. So firstly, it binds to the target receptors on the outer membranes of neutrophils and macrophages. So that's our first line of defense. And of course, our natural killer cells, which is the kind of cell that bridges both of the innate and adaptive immune systems. This then triggers a chain reaction, which produces an increased immune activity. Now, remember going back to the Th1, Th2 diagram, beta-glucans stimulate the Th1 part of your immune system. So this is the part that is slightly more inflammatory, slightly more aggressive, and it involves fighting viruses, cancer, intracellular yeasts and intracellular pathogens. So it does this through potentiated ability of neutrophils and macrophages to engulf and destroy. So it boosts the ability of these innate cells, and the breakdown of the beta-glucan inside the macrophage potentiates complement. So it triggers the complement proteins and their actions. These then stimulate signaling proteins such as interleukin-1, which raises body temperature. So this would be your fever and stimulates growth of disease-fighting cells. Interleukin-2, which promotes the development of T regulatory cells. So this is where it's now moving into our adaptive immune system cells. Interleukin-10, which elevates anti-inflammatory signals. So you have a bit of a balance with the Th2, and lymphokines. So this is the Evita supplement. This is what it looks like, and I will read out. We've got a slide at the very end with the ingredients in detail, but so it's got beta-glucans, 250 milligrams per capsule, recommended at 1 capsule per day. 7.5 milligrams of zinc, 3.75 micrograms of vitamin D3, but that's about 150 IU, international units, and then it has 1.05 milligrams of vitamin B6. So the way in which Vitae come up with their formulations of supplements is so it works in a complementary way. So these other supportive nutrients, so the vitamin D3, the zinc, the B6, they're supporting the action of the beta-glucan, which is the kind of predominant active ingredient in this particular supplement. So this is just an infographic which shows the way in which beta-glucans and Amino Vita in particular improves your immune system barrier day to day. So this green line that's kind of, going up and down throughout the day, if the time scale is, morning to evening, these are your potential pathogen exposures, and the barrier is basically ramped up. So without Amino Vita, or without an immune kind of stimulating supplement, then you may be more predisposed to getting an infection from these pathogen exposures. Okay, so the main route is in which the beta-glucans affect the immune system is via the complement system. So they're agonists of the C3 receptor of neutrophils. So they provoke the priming of neutrophils, increasing their effectiveness against pathogens. So we've got a really good little diagram here. So we've got the neutrophil, the white blood cell here, and then these kind of red arms that are situated on the outer part of the neutrophil. These are the C3 complement proteins. Now I've got a pathogen which already has been tagged by antibodies, and the Amino Vita in the diagram on the far right, this little green bit here, this is the beta-glucan, and this potentiates the ability of the C3 complement to attach to the pathogen. So yes, so the C3 receptor on the neutrophil is agonized by the beta-glucans to be more efficient at detecting pathogens, and therefore they would be able to be destroyed by other immune cells. So the way in which the beta-glucan is digested, beta-glucans are absorbed in the ileum through the intestinal villi until they reach the Peyer's patches. And once they're there, the beta-glucan traverses the M cells and travels the gastrointestinal tract, moving towards the rest of the immune organs. So on the bottom right here, we've got a diagram of an M cell. So M is short for microfold cells, and they're part of the gut-associated lymphoid tissue, the GALT. So any antigens from the digestive lumen are transported through these cells in order for them to be exposed to cells of the immune system, either in tissue fluid or in the blood. So this is what it looks like under magnification. So we've got the beta-glucan absorbed in the ileum through the intestinal villi until they reach the Peyer's patches. So that's number one. And then once they're there, the beta-glucan traverses the M cells, the microfold cells, and travels through the gastrointestinal tract, moving towards the rest of the immune organs. So that is number two here. And then the M cells transport beta-glucan particles from the intestine to macrophages located in the pocket-like structure underneath the M cell. So the beta-glucan binds with the macrophage, which starts a chain reaction of events. So the macrophage digests the beta-glucan and breaks it down into smaller pieces, which then sends signal molecules to other neutrophils. So the neutrophils are primed, which increases their effectiveness to fight and attack pathogens. So moving on now to the other ingredients in Evita. So vitamin D. So we've actually already talked about vitamin D a little bit when we were talking about the Th1, Th2 balance. So vitamin D is a modulator of that balance. Vitamin D receptors are found in most cells, and the sensing of pathogen-associated molecular patterns via the toll-like receptors triggers production of antibacterial peptides. Clinical studies have confirmed vitamin D's role in the modulation of the innate immune system, but it's also indicating that it may be a regulator of adaptive immune response. So this is when it comes into both autoimmune and inflammatory predisposition to diseases. It elevates monocytes' function of killing bacteria as well. Now, another thing that it does, it downregulates hepcidin expression by reducing iron concentration levels. So, as we know, iron is used as a bacterial, as a source of growth for bacteria. So whenever you have an active infection, iron is taken out of the bloodstream, and vitamin D has a role to play in that process. It also has the ability to balance self-tolerance by limiting extreme response of the adaptive immune system. So this is the Th1, Th2 balance. Adequate levels are required for B cell and T cell immune response, but unfortunately vitamin D levels are often very low, particularly in certain groups. So at-risk groups, people with darker skin, people who are not exposed to sunlight on a day-to-day basis, children and the elderly, as older skin doesn't make as much vitamin D. So now moving on to vitamin B6. So the active form of B6 is pyridoxal 5-phosphate. So it's also called P5P, and this is a cofactor for more than 150 enzymatic functions in the body, which include the immunomodulating pathways. Vitamin B6 deficiency affects both humoral and cell-mediated immune responses, which means that lymphocyte maturation is altered. So lymphocytes are part of the adaptive immune system, and also antibody production is indirectly impaired. So this means that the plasma B cells won't be as effective at producing antibodies. And interestingly, research is being undertaken at the moment to assess its interaction in cancer. So now zinc. So zinc is a really critical mineral for so many different pathways in the body. But unfortunately, levels of zinc are very low. It's quite common to have low zinc now. It's essential for cell maturation, differentiation, and proper function of immune cells. and it reversibly binds to regulatory sites that influence signaling pathways. So during the acute inflammatory stage of an infection, zinc is transferred out of the serum, so out of the blood, into the organs, especially the liver. So zinc is similar to iron in the same way, because zinc is used by some pathogens and bacteria in order to grow and replicate. So this removes zinc availability to invading pathogens, and the removal of zinc from plasma, from blood plasma, acts as a danger signal to immune cells. Now, because of this, prolonged inflammation can cause hypozincemia, so a lack of zinc, causing tissue injury, so liver, lung, and spleen in particular. It also adversely affects the maturation of B cells and T cells because, as we know, zinc is crucial in the growth and development of cells, and it disturbs the it disturbs the Th1 Th2 ratio, which results in a Th2-driven allergic reaction. It reduces the natural killer cell function, reducing the MHC targeting on cells. Now, MHC is a major histocompatibility complex, which is basically a protein structure that helps lymphocytes recognize self and non-self. So an increased intake of zinc has been shown to be beneficial for an impaired immune system. Now, we've got a number of clinical research studies to go through, which show the beneficial effects of beta-glucans, yeast beta-glucans specifically, on the immune system. So this particular one is based on 162 healthy participants, and they received 900 milligrams of insoluble yeast over a course of 16 weeks. So what they found was that the beta-glucan reduced the number of symptomatic common cold infections by 25% compared to placebo. So the symptom score was 15% lower in the beta-glucan group, and they also found that beta-glucan significantly reduced sleep difficulties caused by the cold infection. So yeah, the present study demonstrated that the yeast beta-glucan preparation increased the body's potential to defend against invading pathogens. Now, this second study is a review study, so it's a comparison of in vivo and in vitro investigations, but the overall conclusion is that beta-glucans are safe and have an immune strengthening effect. So one of the really great things about using beta-glucans is that they have a really good safety profile, and they're safe to take with most prescription medications. Obviously double check, do your own research before you recommend them, but one study found that yeast-derived beta-glucans, if you took 15 grams daily for 8 weeks, they could be taken safely. Obviously, a lot of these studies show a dose of 250 to 1,000 milligrams is recommended. So 15 grams is much, much more. And lots of studies have shown that there are no adverse effects. Now, there are a few caveats of this, because as the method that beta-glucans work on, the process that they work on in the immune system, means that if you're taking any immunosuppressants, then it may counteract the effects or decrease the effects of them. So if anybody is taking immunosuppressants, and that includes corticosteroids as well, then beta-glucans and any immune stimulating supplements would not be recommended. Similarly, in autoimmune conditions, beta-glucans are not recommended. So I think with this one in particular, it's best to be safe and use your own judgment as practitioners. And if somebody is showing a particularly Th1 dominant profile, then beta-glucans wouldn't be the best thing to use. I mean, if they have something like celiac disease but they also are prone to recurrent infections, and maybe they also have an allergic picture, then maybe it would be something to look into. Again, I'll leave that to your own discretion, but the practical applications of the beta-glucans are to improve infections and from viruses, bacteria, recurrent infections, and allergy. We'll go through that again at the very end. So this study takes 299 generally healthy men and women with quite frequent episodes of upper respiratory tract infections, and they took 900 milligrams of beta-glucan daily for 16 weeks. So the results of this were that the severity of the upper respiratory tract infections was less pronounced in the beta-glucan group. The severity of physical symptoms was significantly lower, and the reduction of severity was accompanied by a significant increase in the joy subscore of the perceived stress questionnaire, which is always good. There was a reduction in blood pressure as well, which is interesting to note. So on this particular study, it didn't affect the initial infection, the chance of people getting the infection. It improved the speed and the effectiveness of the response. And this is another example of an upper respiratory tract infection. This study in particular, this was done on marathon athletes. So another really good application of beta-glucans is people who have maybe a depressed immune system, so people who are highly stressed, or athletes in particular. Quite a few studies have been done on marathon runners. And this is because it stimulates the immune system where it may be chronically suppressed. So in this case, relatively low doses, so 250 or 500 milligrams beta-glucans for 4 weeks post-marathon event. So at 2 weeks, the upper respiratory tract events were reported by 68% of participants in the placebo group, whereas only 32% and 24% in the beta-glucan group. So obviously the effectiveness goes up with the higher amount of beta-glucans that are taken, and also reported reduction in fatigue, confusion, tension, increased vigor in the beta-glucan groups. So another really good application is people who are training for marathon or another intense sporting event, athletes, or people who are highly stressed. Another study on firefighters who took beta-glucans had a 23% reduction in upper respiratory tract infections. So it's a really good for those. So this is one study which is done on allergy sufferers. So this is ragweed allergy sufferers. So 250 milligrams. So this is again quite a low dose. This is the same dose that's in, comparatively in these studies, this is the same dose that's in Evita. And in this case, it reduced the total allergy symptoms by 28%, symptom severity by 52%, reduced tension, depression by 45%, anger, fatigue, confusion, and similarly to the earlier study, it decreased sleep problems, reduced nasal symptoms, eye symptoms, quality of life. So basically every measure of allergic symptoms, it has improved. And here is, this is actually a mouse study, so this is an animal study, but this shows that beta-glucans could potentially be useful as an oral supplement for some asthma patients. It would probably need to be combined with other therapies that target other aspects of the disease, was the conclusion of this particular paper. Okay, so we've almost got to the end now. So this is just a very quick overview of the other ingredients in Evita, and there are so many different studies for these. So vitamin D, zinc in particular. B6 isn't one of the nutrients that you think of first for immune system health, but it provides a really good complementary complementary role. So what is Evita indicated for? So all members of the family, there's a children's version of Evita, which is lower doses of all of the same nutrients. 30 minutes before breakfast, which is the studies that Evita has been run with. Treating recurrent infections, combating colds and flu, virus and bacteria, minimizing the lowering of defenses in periods of high stress, and helping to reduce the adverse immune effects and improve mood in athletes. Additionally, and quite importantly, reducing symptoms of seasonal allergies. So as we discussed, not considered suitable for anyone taking immunosuppressant drugs, and that also goes for autoimmune conditions if it's a particularly strong, autoimmune picture. Okay, so we have one case study to end the webinar. So a male, 29 years old, presenting with a fever, pain on swallowing, swollen lymph nodes, examined by a GP and found to have enlarged tonsils, swollen lymph nodes in the neck, and enlarged liver. So a viral infection is diagnosed. So the initial blood test results are a leukocyte count of 16,000. This will become relevant when we see the next slide because these figures all decrease. AST and ALT are liver enzymes which indicate damage to the liver, so this would be the viral infection in the liver. So AST is 170, ALT 200. Epstein-Barr here, the IgM antibody is positive and IgG negative. So the treatment given here is rest, something to reduce the fever, multivitamin, Evita, one with breakfast and one in the evening, and also Reconnect, which is another Vitae supplement which has coenzyme Q10 NADH, a small amount of vitamin C and serine. So all supportive supplements to help give the patient more energy. Okay, so 30 days after blood test results, the leukocyte count has gone down from 16,000 to 9,000. AST and ALT, they were 170 and 200, and now they're at 90 and 98. Now Epstein-Barr, so the Epstein-Barr virus is glandular fever. So the IgM is still positive, and now the IgG is positive. So in this graph down here, this shows the progression of the production of antibodies. So IgM is the first antibody to be made by the body to fight any new infection, and IgG is produced in later stages. So it's the most abundant type of antibody, and it's found in all bodily fluids. So revised treatment here is multivitamin, a slightly lower dose of Evita, only one capsule, and the same with Reconnect, one with breakfast only. And after 90 days, so 3 months later, his leukocyte count has gone down to near normal, so 5,600, as have the liver enzymes. And now the IgM antibody is negative and IgG positive, which shows the beginning of the resolution of the infection. So this, as promised, is the overview of the Evita supplement. So we've got the beta-glucan 250 milligrams, vitamin D3, this is 3.75 micrograms. As I said, I think that's 150 international units. B6 1.05 milligrams and zinc 7.5. So with all of these, although it's indicated to take one capsule, it would be safe in a acute infectious stage to take 2 capsules, as the case study showed. And then we have Evita Kids. So this is a modified amount, and it's also in sachet form. So it makes it much easier for children to take it, increasing compliance. So brings us to the end of the webinar. Thank you so much for sticking around. I hope it was interesting. If you have any questions or comments, please email them across on the email address here, and I'll do my best to answer. So Evita and the other Vitae supplements are available on the Vitae website, and they're also available on Natural Dispensary as well. Okay, thanks again and good night.